Hello, Algebra students. This lesson is going to be our first lesson on our final units. The name of this lesson is a different kind of change because this lesson is going to be looking at a different type of relationship. So far, we've talked about linear equations in algebra. Last unit was on exponential equations. There's going to be one other type of relationship we learn about in this final unit, and you are going to learn what that relationship is today. So to get us started, that's another one of these what do you notice, what do you wonder, warm-up questions. There are 3 tables on the screen. I'm going to have you pause the video here and see if you can notice anything about those 3 patterns. If you have any questions about those 3 patterns, come back to the video when you're ready to discuss. All right. Hopefully you looked over those warm-up questions. Before we jump into the math, I do want to point out the reminder, 4 weeks left. This is our final unit in algebra. And so once we finish this unit, we're going to be at the point in the class where we start doing review, the final exam, and we get to finish up. Our 3 patterns in these tables. In the past, I've had some students notice this first one here is going up the same amount each time. We're going up by 5 every single time our x goes up by 1. And so because of that constant addition, you might have also labeled this first one as a linear relationship. For our second table, in the past, some students have noticed this one is not going up the same amount. Here we are doubling or multiplying by 2 every single time. You go up by 1 on the x values, and because we have that constant factor, that growth factor, we can refer to the second one as exponential. And then when I ask that question, what do you wonder? Usually what students wonder about is this last table here. They ask I'm wondering what the pattern is here. If you look at those values, we can see it's not going up a constant amount because here it goes up 3, but then here it goes down 1 and then down 5. And then to go from 5 to -4, you're going down 9. So we're seeing here this isn't the same. So it's not linear, but there's also not a constant multiplication. Just the fact that it goes up and then goes down, right? That tells me I'm not constantly multiplying by something. So usually when I ask that, what do we wonder? It's usually about this last table is what is happening. I notice it's increasing and then decreasing, but I don't see a real pattern here. And you may be able to predict this last table here is what we are going to be investigating in this lesson and in this unit. Our goal for this particular lesson is by the end of this that you are able to describe a new pattern of change. And to start us off with this unit and understanding this pattern, we're going to start with a lot of series of pictures here. So on the screen, there are 2 different patterns. The first one, step 0, remember we use that number 0 as a starting point. So pattern 1 starts with 1 dot, and then it continues in growing in this pattern. Pattern 2 is starting with nothing, and then it continues to grow in this pattern. And so the questions I'm going to have you think through here are looking at the 2 patterns of dots. Can you identify how the number of dots in each pattern is changing? And then thinking through, I need my face to move. Nope. Thinking through how would you find the number of dots in the 5th step for each pattern. So if I asked you how many dots there are in step 5 for pattern 1 and for pattern 2, could you give me a number? Go ahead, pause the video now to give yourself time to look over the patterns and see if you can identify how the number of dots in each pattern is changing. As students think about how it's changing, sometimes it helps to put a total with them. So notice for step 0, we have 1 dot here, and then 3 dots, and then 5 dots, and 7 dots. Every single time, it's whatever the picture looks like before, but we're just adding 2 dots to the end of the picture. So notice our step 4 then, it would look like this one just with 2 dots at the end. For pattern number 2, we start with 0, and then this one here looks a little different. pattern 2 isn't adding the same amount of dots, and I can put some numbers here. We go from 0 to 1 to 4 to 9. Here our pattern is a 1 by 1 square, and then a 2 by 2 square, and a 3 by 3 square. So you might guess step 4 would look like a 4 by 4 square. We're going to answer B on the next slide for how many are in the 5th step. We first need to be able to identify this pattern though. The first one, we're adding 2 dots each time. And then pattern 2, there's not adding the same amount, but it's this expanding square. It's a square that keeps getting bigger and bigger. So I'm just going to write expanding square here to go with the second pattern. And here we keep adding 2 dots each time. So keeping those patterns in mind, we'll come down to this table and we are going to go ahead and complete the table. So we had already started doing this. We said for pattern 1, we started with 1 dot and then had 3, then 5, then 7. Now I don't have a picture for step 4, but you might already know how many dots there are based on that pattern we identified of each time you're just adding 2 dots at the end. We know that step 4 would be the picture we had before. This is step 3, and then we're just adding 2 more dots. So that would get us to 9. And then we're just continuing that pattern of adding 2 each time. So step 5 would be 11. Now, notice I'm jumping from step 5 to step 10. Any idea how many 10 would have? Well, for 10, you could go ahead and figure out step 6, step 7, step 8, step 9, and then get to step 10. Or you can think a little bit more about what we're doing here. For example, for step 2, I ended up adding 2 sets of these 2 dots. So I had to add 2 sets of my 2 dots to what I started with. And I started with 1 there. Or for step 3, I ended up adding 1, 2, 3 of those pictures of 2 dots that we were adding to that starting point here, to the 1. So when we get to step 10, you could do step 6, 7, 8, 9, and 10, or you could just stay for step 10. We're starting with that 1 dot still, but then by step 10, I would have added the 2 dots that I've got in that yellow circle there 10 times. And if you do that math, it leaves you with 21. And so especially if you were writing out any math to get these totals, we notice that every single time we are starting with 1, and then I'm adding 2 dots times whatever the step number is. So if I asked you about step 100, I definitely wouldn't want to draw this or continue my table from step 10 to step 100. I just know that we're starting with 1 dot and that I'm adding the 2 dots 100 times to get that total there. So this first pattern I could describe by 1 plus 2n. I start with 1 and I add 2 dots each time. Now what about pattern 2? With pattern 2, we had already said earlier that we're starting with 0. And then in step 1, I've got a 1 by 1 square for a total of 1. Step 2, I've got a 2 by 2 square for a total of 4. Step 3, I've got a 3 by 3 square for a total of 9. How many do you think we would have in step 4? Well, step 4 would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. I would have 4 on each side of that square. And so we would have 16 there. What about step 5? Before you give an answer, think about what math would we do. I don't want to draw step 5 this time. I want to think about what math we're doing here. Well, to get to that 16, I've got these 4s here. To get to 16, I could have done 4 times 4. Or you could have thought of that as 4 squared. So for step 5, I could be doing 5 times 5 or 5 squared to figure out that there would be a total of 25. And that multiplication or exponents we're writing down, you could do for these others too. We could do 3 times 3 or 3 squared, 2 times 2 or 2 squared to get all of these answers. So when we get to step 10, what math would that one be? Well, step 10, that would be a 10 by 10 square. And so the math I would need to do is 10 times 10 or 10 squared, whichever you prefer. And that would give us 100. So again, noticing here, there's a pattern going on. Every single time, whatever the step number is, I'm multiplying it by itself. So if we do that pretend step 100 again, for step 100, because the step is 100, I would be doing 100 times 100, or 100 squared. 100 squared means 100 times 100. So now let's make the jump. This is what we want to be able to do. If we've got step n, and I don't know the step number, I still know what math I would be doing. For step n, just like for step 4, we did 4 times 4. Step 5, we did 5 times 5. For step n, I would be doing n times n. Or you can think of that as for step 4, we did 4 squared. For step 5, we did 5 squared. Step 10, we did 10 squared. For step n, we would be doing n squared. To summarize what we're seeing here, this first pattern, we were adding 2 dots every single time. That gave us this table here and that expression at the end, 1 plus 2n. This first relationship here, you should be familiar with this. Say it with me. This is a linear relationship. It is going up the same amount every single time. And look at that expression we've got. That's what linear relationships look like. For this second one here, it may be tempting to say exponential. Maybe you want to say exponential because we see an exponent. But remember, exponential things have that constant multiplication. And when I look at our table, and I move my face, I'm not seeing a constant multiplication. I know to get from 1 to 4, I would need to multiply by 4, but I'm not multiplying by 4 each time, right? And when I look at the expression we wrote, exponential relationships have the variable as the exponent, but here I don't have that. Here I've got the exponent 2. So this is not an exponential relationship. This is something different. There's one final thing we're going to do with this, and that's match it up with a graph. And so I'm going to come down here. Now this first one we already said is linear, so you should be able to predict what this first one looks like. If it's linear, I know it's going to be a straight line. And when we go to graph it, I know step 0, we said we're starting with 1. And then we said we're adding 2 each time. So step 1, we had down that there was 3. For step 2, we know that there's 5. Step 3 would be 7. Step 4, 9. Step 5, 11. I'm just adding 2 each time. And sure enough, we predicted that it would be that straight line there. If I go ahead and draw a line through it, we get a graph that looks like this. I'm going to quickly point out that we could connect this back to the expression and the work we had done on linear equations. My y-intercept is at the number 1, and it's going up 2 each time. That's our slope. The second one, that was our expanding square pattern. So remember, step 0, there was no square. Step 1, there was a 1 by 1 square. Step 2, 2 by 2. Step 3, 3 by 3. And so when we found the total number of dots, we saw it started at 0. And then step 1, there was 1 square. 2, there was 4 squares. 3, there was 9 squares. 4, there were 16 squares. Step 5, there was 25 squares. And then for step 6, I can't even put it on this graph. It is at 36 because it would be a 6 by 6 square. So 6 times 6 is 36. That would be somewhere up here. And if I go to draw a line through this, I can't use that straight line because I see it is curving. I'm trying to draw that as neatly as possible here. Now we've seen other graphs that curve. Our exponential graphs curved, But this is not the same as an exponential graph for the same reason we said earlier. I'm not multiplying by a constant amount. Here, if we were multiplying by 4 on an exponential graph, that next number would be 16, not 9. So it is curving, but not in the same way. It is a different relationship. There's one other pattern we're going to look at, and then we're going to summarize what we're seeing here. So here's another pattern of squares. Step 1, step 2, and step 3 are given to us. The first question I want you to think through is the number of squares here growing linearly. And then, as always, be able to explain how you know. Go ahead, pause the video here and see if you can identify if it's growing linearly. To identify if it's growing linearly, it might help us to identify first how many squares are in each step. So step 1, I see 3. For step 2, I see 6. And then step 3, we have 11 there. So just based on those first 3 numbers, that is enough for me to say if it's growing linearly or not. What did you say? Well, to grow linearly, we need it going up by the same amount. And so if it was linear, notice 3 plus 3 gets me to 6. Linear would be the same amount here. But here, it didn't go up the same amount. Here, it went up by 5 squares. So that part in pink is enough for me to say, no, it's not linear. And for our explanation, it's not linear because it does not increase by a constant amount. So there must be a different pattern going on here. For the next one, we are going to be completing this table, but in order to complete the table, it helps to be able to first figure out what the pattern is. And so I'm going to have us actually draw a picture for step 4 before we get to that table here. Looking at this pattern, step 1, step 2, step 3, step 4, do you have any guess about what step 4's picture would look like? As you're trying to figure out what the pattern is here and what the picture would look like, if you're really confused, sometimes it helps to look at the step number and see if you can find a connection. For example, step 2, do you see anything about this picture where it changed from step 1 that has to do with the number 2? Step 3, do you see anything in this picture that has to do with step 3? Because step 4 then would follow that same pattern. It also helps to break down the picture a little bit into what's remaining the same and what is changing in the pattern. So for example, up here with this one, the entire picture was changing every single time. Step 1, we had a 1 by 1 square. Step 2, we had a 2 by 2 square. Step 3, we had a 3 by 3 square. But in pattern 1, yeah, there was something changing. I was adding those 2 dots every single time, but every single picture started with this first one, right? So there was that part that remained constant. So looking at this pattern here, I separate it into 2 parts to the picture. I notice every single time, especially looking at step 2 and step 3, there's these 2 squares on the end. I know step 4 is going to have 2 squares on the end, same as these. In step 1 too, I see it there. There's 2 squares on the end every single time. And especially after I color those in, we start to see the part that's left. Step 1 has 1 square. Step 2 has a 2 by 2 square. Step 3 has a 3 by 3 square here. And so step 4 then, we're going to see that same thing is going to have a 4 by 4 square. And let me go ahead and fill that in. I'm going to use the same words as earlier. Here we've got that expanding square. We've got a 1 by 1 square, then a 2 by 2 square, a 3 by 3 square, and a 4 by 4 square. And so when we go to figure out these total amounts, I'm going to use that to help me out. Here I see there's a 4 by 4 square, so I know to get that total, I'm going to have to do 4 times 4. But then I also need to add these 2 extra ones in. So I'm going to have to add 2 to get that total. So 4 times 4 gives me 16, and then 16 plus 2 tells me there must be 18 in step 4. So when we move down to the next slide where we're filling in that table, if you need to draw some pictures for yourself, absolutely do that. I would continue to break the picture into these 2 parts here. That part in the middle that I did in yellow of that expanding square, and then those 2 extra squares on the ends that I had been doing in green. So coming down here, here's that table. I'm going to have you go ahead, pause the video, and see if you can fill in that table now. So these first 4 we had already done above. We had said step 1, there was a total of 3. Step 2, there was 6. Step 3, there was 11. Step 4, we said there was 18. For step 5, remember I'm breaking it down into 2 parts. So for step 5, I would have a 5 by 5 square. And so to find how many total are in that 5 by 5 square, I'm going to do 5 times 5. But then there's also those 2 on the ends. There was every single time those 2 that we had to go add in. And so to get that total, 5 times 5 is 25, plus 2 gets me to 27. For steps 10 and 12, it's going to be similar. For steps 10 and 12, I'm also going to do it like step 5 where I don't draw all those individual ones. But I know for step 10, there would be that 10 by 10 square in the middle. And so to figure that out, I'm doing 10 times 10, or since 10 times 10 is the same thing as 10 squared, maybe you've been thinking about it that way. And then every single time, we're adding those 2 on the end. So I would be doing that 10 squared to get the big part, and then plus 2 for those 2 on the end. 10 squared is 10 times 10, which is 100, and then 100 plus 2 is 102. Step 12 would be similar, where there would be that big square that is 12 by 12. That does not look like a square. And then I would be adding in the 2 on the ends for our plus 2. And when you do out that math, 12 squared, or 12 times 12, gives you 144, plus 2 is 146. I've been writing out the math like this so that we can see again there's that pattern. Every single time we were multiplying the step number by itself to get that expanding square part I keep talking about. Step 3 was that 3 by 3 square. Step 2 was a 2 by 2 square. Step 100 would be a 100 by 100 square. There's that expanding square part, which I've been filling in the table in blue. But then every single time there was also those 2 squares on the end we couldn't forget about. And so every single time after I found out how much that expanding square had, we kept adding in 2 each time. And so when we get down to the end, to represent it for step n, if I didn't know the step number, I know every single time, whatever that step number is, that's telling me how big that square is in the center. So for step n, it would be n times n, or n squared, however you've been thinking about it. And every single time, we had to add in those 2 extras at the end. So for step n, if you wanted to think about what step n would look like, let me make some room. Step n would have an n by n square in the center, same as these up here. And then there would be those 2 squares at the end, same as all the others. So we finish off our table by saying this pattern here can be described as either n times n plus 2 or n squared plus 2. So when you think about this pattern here, is this pattern growing exponentially? I see an exponent. No, it's not, for the same reason we said above. If it was exponential, I would need to see a constant multiplication. And even here at the beginning, 3 multiplied by 2 gets me to 6. But notice I'm not doing that every single time. If I was multiplying by 2, this should be 12 here. And so we don't see that constant multiplication. And when we look at our expression here at the end, N squared is not exponential. We had talked about exponential things look like having a number that you're starting with, maybe like 100, and then you're multiplying by something, and your variable is up here. It's the exponent. In here, we do not have that. And so what is this new expression? We've said it's not linear, it's not exponential. This new expression where you have a number multiplied by itself, or n squared, this new relationship where you have this expanding square in our pattern, we call this a quadratic. What we just wrote above is a quadratic expression. Quadratic expressions fall into the form ax squared plus bx plus c. And the part of that I really want to highlight is this part here with the x squared. A quadratic expression is going to be anything that has an x squared in it, or n squared or y squared. We know the variable is squared. So above, we had written n squared for that first pattern where you had nothing, then you had a 1 by 1 square and a 2 by 2 square, and then a 3 by 3 square. That was n squared. That was a quadratic. And then this one we just did, n squared plus 2, where we had our 1 by 1 square with 2 on the each side, and then we had, whoops, that is not 2. We had our 2 by 2 square with 1 on each side, and then we had a 3 by 3 square with 1 on each side. This pattern here of that expanding square plus 2 is also a quadratic. Both of these are quadratic because we have that variable squared in them. And so to summarize now, the three relationships we look at in this class, the first one we had started in pre-algebra, and we talked a lot about in Algebra 1A as well. That first one was a linear relationship. Some of the things we had connected to linear relationships was this formula here. And so, for example, if I gave you y equals 2x plus 1, this told me our y-intercept, or our starting point, was at 1, and then this was our slope. It said it was going up by 2 each time. And so when you looked at equations, or not equations, this is a table. When you looked at tables, we would see in that table that those values are going up by a constant amount. Here, every single time, they're going up by 2. And because they're going up by a constant amount, we said when you go to graph it, it looks like a straight line. It's going up the same amount every single time on the graph. In our last unit, Unit 5, we talked about exponential relationships. And exponential relationships look something like, I'm going to make up some numbers here, something like this. Similar to our linear equations, we could tell the starting point. So this was whatever the starting value was, or when x is 0, the starting amount. And then this was how it grew. We called this our growth factor, and it told us that if we were looking at a table, that if we're starting with 5, we're doubling it or multiplying by 2 every single time. And so we got tables that looked something like this, where you had that constant multiplication in it. And we learned that when you graph those exponential equations, if it's got a growth factor and it is increasing, it increases with a curved line. But then we also saw they could decrease with exponential decay, and it looks something like this. I guess I should add too, linear equations could also decrease, but it's still decreasing by the same amount. This new one that we are going to be learning about in this unit is quadratic. And so far we know quadratics fall into the form ax squared plus bx plus c. With quadratics, that most important part here is going to be that x squared part. Somewhere in the equation or expression, you're going to see x squared. We don't know too much about quadratics yet, but we do know that if you're looking at a picture to go with the pattern, it's that expanding square. For step 1, you might see a 1 by 1 square. Step 2, you see a 2 by 2 square. Step 3, there's going to be a 3 by 3 square somewhere in it, and that pattern continues until we get to step n, which is an n by n square. We start quadratics with these pictures of different patterns because it really gives us a better understanding of how it's growing over time. And we are going to continue to look at these patterns tomorrow. And so to summarize and to practice everything we've learned in this lesson, here is your cool down. I've got 3 different patterns here, and your job is to identify which pattern is linear, which is exponential, and which is quadratic, as well as thinking through how you know and the why behind it. Go ahead, pause the video, and try this last problem here. This is a great way for you to check in and see how well you understand this new topic. As you finish up this problem here, a good way to start for a lot of people is putting the total number of dots in each pattern below it. So here, step 0 has 0, and then step 1 has 2, step 2 has 4, step 3 has 6. When you've got those totals there, it makes it a little easier to see how it's growing. For example, once I put those totals, it makes it a lot easier for me personally to see each time we're adding 2 dots. Plus 2, plus 2, plus 2. And I can see that in the pattern. Here we have no dots, so I added 2 to it. And then I'm taking the picture from before and adding 2 more dots. I'm taking the picture from before and adding 2 more dots. I can see the 2 that just keep getting added on the end. And because we're going up by a constant amount and we are adding 2 each time, that makes this a linear pattern. For pattern B, I'm going to do the same thing and put the totals at the bottom. Here I've got 1, here I've got 2, here I've got 5, and then 10. As I look at those numbers, I don't see us going up by constant amounts. And when I look at the pictures a little more closely, I also can tell I'm not multiplying by a constant amount. 1 times 2 gets me to 2, but 2 times 2 doesn't get me 5. So I've ruled out linear. I'm not adding the same amount. I also said it can't be exponential because I'm not multiplying by a constant amount. This right here is our new relationship. Looking at these for step 1, I see a 1 by 1 square. Step 2, I see a 2 by 2 square. Step 3, I see a 3 by 3 square. We've got that expanding square here again, which makes this a quadratic. Every single time we've got that expanding square, and then we're just adding an extra 1 to the total. This final one here, let me put my totals. Step 0, we have 1. Step 1, we've got 3, and then 9. And when you add all of this up, it is 27. Looking at those numbers, I can tell we're definitely not adding by the same amount, but those numbers do make it a little easier to see each time I'm multiplying by 3 to get to the next one. Each one of these pictures, I'm taking what I see in the previous picture and then drawing 3 of them. So I'm taking what I see in the previous picture and drawing 3 of them. I'm taking what I see in the previous picture and drawing 1, 2, 3 of them. And we've got that multiplying by 3. So because I'm multiplying by a constant amount, that makes this final one exponential. I really like this question because it's great practice on those 3 patterns we have learned about. You could even, if you want, write expressions for each of these. For example, this first one here is linear because I can represent it as 2n if we make n the step number, right? If I jump to step 4, I'm just taking 2 times 4 to get that there's a total of 8. For our exponential pattern, I see I'm starting with 1, and every single time I'm multiplying it by 3. So I'd be multiplying it by 3 how many times? Well, whatever our step number is. So 1 times 3 to the n power, or you could also just write that as 3 to the n power. For example, for step 4, I'd be taking that 1 dot I have and multiplying it by 3. 1, 2, 3, 4 times. And so that would be 3 to the 4th power, which equals 81. But this new one, our quadratic one, that's the big one for today. I'm noticing each time I've got a 1 by 1 square, a 2 by 2 square, a 3 by 3 square. So for step 4, it would be a 4 by 4 square, or for step n, it would be an n by n square or n squared. But then every single time I also had to add that 1 at the beginning. So n squared plus the 1 extra one we had each time. The part in red is extra, and that's going to be the part we really practice in tomorrow's lesson. This is a great start, though, for this unit. I hope you enjoyed this lesson video, and make sure you come back for the next one. Bye, y'all.